Okay guys, so this is the second video for chapter 10, gases. I just introduced in the previous video the idle gas law, which I'm right up here, PV equals nRT. Okay, that's the normal way that it's presented. Again, there are four variables there and one constant. Most problems that use that equation, they're going to give you three of the variables. You should know the constant. If you plug in those four things that you know, you should be able to solve for the one that you don't. Okay, there will be problems later we do where they get a little bit more complicated with that, but really that's the main idea of it. Okay, now I'm going to use that equation though to derive my second equation, which is called the combined gas law. So I'm going to go back to the form of the equation I had initially, where I had everything on the left side except R. So if I divide N and T over, I get PV over NT equals R. So for any gaseous sample, if I have a pressure, a volume, a moles, and a temperature value, if I plug them all in, I know it's going to equal 0.0821. That's just the universal gas constant. It always works out. So, example I usually use in class when there's people in the room. If I had a balloon here with me that's full of helium, I could measure the pressure, volume, moles, and temperature, plug them in, and get the value of R. Let's just say those are my initial conditions. If I'm standing in the classroom and I measure the values right now, let's call that P1, V1, N1, and T1. It's all the values being measured at one instance. Okay, but then let's just say I leave the classroom, I hop in my car, I go drive up in the mountains, maybe I go up to the top of Brasstown Bald. At that point, if I look at my balloon, it'll have changed some. Okay, up at the top of Brasstown Bald, it's probably not the same temperature. Most of the time it's a little bit cooler, so my temperature goes down. My air pressure is also different because air pressure, as you go up in altitude, the atmosphere gets thinner, so there are fewer collisions of molecules, which means the pressure is going to be lower. That is something you should know. At high altitude, atmospheric pressure is less than at sea level. So my pressure will change, my temperature will change, and if they change, then chances are the size of the balloon is going to change too, because all these variables are related to each other. Remember, each one, you could say they're either directly or inversely proportional to each other. So the only one that probably hasn't changed, if I assume that my balloon is tied off, and it's been a pretty short period of time between being here and driving up in the mountains, maybe an hour or two, pretty much the amount of gas in the balloon should be the same. So the only one that's probably going to stay the same is that. But regardless, if I go up to the mountain and then remeasure my pressure, volume, moles, and temperature, they are mostly going to be different from my initial values. But if I plug them in the same equation, it could still equal R, because any gaseous sample, plugging everything in, will always give me R. So I'm going to set up another equation on this side. R equals my initial PV, N, and T. It's also going to equal my final P2, V2, N2, and T2, which are now the pressure, volume, moles, and temperature readings under different conditions. I've changed something, I remeasure all the values, so this is my second set of data points. But guess what? Those values are still going to equal R, and in algebra, a long time ago, you learned that if A equals B and B equals C, then that means A equals C. I think that was called the Associative Property. So from that, I'm going to be able to take this side of the equation and this side of the equation and set them equal. So that's going to give me my combined gas law, P1, 1V1 over N1, T1 equals P2, V2 over N2, T2. So I've got my ideal gas law up here. I've got my combined gas law down here. Those are my two fundamental equations that we have to have for chapter 10. I can do almost everything in the chapter with those two equations, at least most of the big things that we're going to focus on. All right, so how would I do a problem like that? Well, again, I've got the worksheet pulled up. This is the chapter 10 combined gas law worksheet. So we'll work a couple of the problems. The first problem says if I have 4 liters of a gas at a pressure of 1.1 atmospheres, what will the volume be if I increase the pressure to 3.4 atmospheres? So, looking at my equation, anytime it has changing conditions. So it gives me an initial volume, it asks me for the final volume. It gives me the initial and the final pressure. So I have 2 pressure readings, I have 1 volume reading given, and it wants the second volume reading. So I'm going to be using P1, V1, and P2 and V2. Okay, now let's look at the whole equation though. So P1, the initial pressure, was given to be 1.1 atmospheres. The initial volume was 4 liters, 4.0 liters. Okay, now I'm just going to worry about the top of the equation at first. My final pressure, P2, is going to be 3.4 atmospheres. And then they didn't give me V2, so that's my X, that's my unknown. Now, the problem, I'll read it again. If I initially have 4 liters of a gas at a pressure of 1.1 atmospheres, what will the volume be if I increase the pressure to 3.4? So I've got my combined gas law here. They mentioned my pressure and volume readings, both initial and final. They never even mention the moles or the temperature. So what do I do with that? Like, I have to kind of decide, how do I address that? If they leave out information, sometimes I have to make some assumptions in order to solve the problem. And this is something that we need to deal with, because they're not always going to give you everything. Sometimes you have to think about it. So when they talk about a sample of gas, pretty much always, unless they talk about adding more gas to the container or taking gas out of the container or gas leaking out of the container or something like that, if it's a closed container, we're going to assume the amount of gas is going to stay the same. Meaning the original measurements, the amount of gas in the container, N1, once I change the conditions, the amount of gas in the container when I make my second set of measurements, N2, is still going to be the same. Now, what is it? Well, the problem doesn't tell me how many moles I have, but let's just make up a number. Let's just say that the moles of gas in the container, let's say it's 10 moles. If N1 is 10 moles and N2 is 10 moles, if I'm dividing both sides of the equation by 10, I can cancel those out and just get rid of them in the first place. There's no need to divide both sides of the equation by the same number. So algebraically, I cancel it out, which means my N1 that should be right here and my N2 that should be right here disappear from the equation. Okay, what about the temperature? T1 and T2. Well, again, they mentioned in the problem that they're changing the pressure and they're measuring the volume. If they don't mention the temperature at all, I'm going to have to assume that it stays the same. Just like with moles, if I had the same value for T1 and T2, let's just say the temperature in the room is 25 degrees Celsius. Well, first of all, if I was going to plug it in, I can't plug Celsius in the equation. I would need to switch it into Kelvin. So 25 degrees Celsius plus 273 would give me 298. You do need to be able to do that. So it's 298 here and 298 here. Well, again, if it's the same number on both sides, it cancels. So essentially, the whole bottom of the equation disappears. That creates Boyle's law. So if you remember when in the first video I mentioned from the ideal gas law, if we do some rearranging, we can get all the equations that we need to do the relationships of Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law. All those laws are contained in this equation here. The rule is, for Boyle's law, he was studying the relationship between pressure and volume. The only way he could actually see how they're related is by holding the amount of gas and the temperature constant. If you hold N and T constant, they drop out. P1 V1 equals P2 V2. That is Boyle's law. When Charles did his studies, he studied the relationship between temperature and volume. And he said, when I increase the temperature, the volume increases. Well, in those experiments, he assumed the pressure was constant, P1 and P2, and he assumed the amount of gas in the balloon was constant, N1 and N2. So in that case, if I cover up P1 and N1 and cover up P2 and N2, that simplifies the equation down to Charles' law. So what I learned is, if I know this full combined gas law here, it eliminates the need for me to memorize Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, or any of those other ones. Okay? So that's what we want to do. With these two equations, I want to be able to solve any problem where we're changing the conditions. This problem that I worked over here, all I need to do, on the bottom, I don't need to put anything, or you can put a 1 there if you want to. But essentially, I just need to solve for x. So I just multiply those two, divide the 3.4 over. That'll give me x. The units of volume here and the units of x are going to be the same because they always have to match. Left side, right side of the equation have to be consistent in my units. My volumes, again, it's preferred that it's liters on both sides, but as long as you're consistent, if they gave you the volume here in milliliters and then this volume was in milliliters, that would be okay as long as you're consistent. All right, so that's the first combined gas law problem. So now let's look down. I'm going to do number 3 now on that Chapter 10 combined gas law worksheet. So I'll read it. A small research submarine has a volume of 1.2 times 10 to the 5th liters. The internal pressure is 1 atmosphere. The internal temperature is 15 degrees Celsius. So they just gave me P1, V1, and T1. Then it says the submarine descends to a depth where the new pressure is 150 atmospheres. That's P2. The new temperature is 3 degrees, so that's going to give me T2. And then it asks me for the volume. What's the volume inside the submarine? So, the one thing it didn't mention at all was the amount of gas. We assume the amount of gas in the submarine, N1 and N2, must be constant. Sometimes they'll tell you that a variable is held constant. Sometimes they just won't mention it. Either way, if it's a constant, we're going to get rid of it. So my equation is going to be P1 V1 over T1 equals P2 V2 over T2. Then I'm going to plug my numbers in. So my initial pressure was 1 atmosphere. My initial volume was 1.2 times 10 to the 5th. And my initial temperature, they gave me 15 degrees Celsius. I add 273, that's going to be 288 Kelvin. So P1, V1, T1 equals, my new pressure is going to be 150 atmospheres. My new volume is what it's asking for, so I'm solving for V2. I'm going to put my X there. And my new temperature, 3 degrees Celsius, converted to Kelvin at 273, that's going to be 276 Kelvin. And again, at this point, I'm not going to do the algebra. I want to move on and get stuff done. But my X value here is what I'm solving for. That's going to be my liters. X equals some number of liters. That's it. Okay, I think that's a good place to cut off from the combined gas.